Hi everyone, I am D Mithun, registration number 24PEC0508, and now we'll be discussing a small lecture video on the topic Introduction to Quantum Ideas. Physics has always been divided into two branches, classical ideas and quantum ideas. Classical ideas are mostly dependent on Newton's laws. It involves the three Newton's laws and explains the majority of the happenings around us, which are observable to the human eye. But on a smaller scale, there are many discrepancies which seem to not align with the Newton's laws, which cannot be explained through the classical ideas. There came into picture the quantum ideas. Classical physics broadly classifies everything into particles or waves, but some things cannot be explained using only a single ideology. So quantum ideas do not exclusively tell about the nature. A wave equation is used to describe about the nature of a particle according to the quantum ideas. Particles and waves are localized. That means their exact position and momentum is known. But quantum ideologies do not localize a particle or matter because there's always a kind of uncertainty in their position or momentum. Classical mechanics are deterministic. They determine a thing blindly, but quantum mechanics are probabilistic in nature, which means they tell about the probability of things happening in a way or probability of things either happening or not. Experimental observations. There are some experimental observations that cannot be explained using classical ideas. Some of them are black body radiation, photoelectric effect, Compton scattering, line spectra of hydrogen atom, heat capacity of a solid, origin of magnetism, incompressibility of a solid, difference in electrical conductivity of metals, semiconductors, and insulators. Quantum ideas has become a very crucial thing in the development of science, in the development of technology, as it gives us a broader spectrum to think about and gives us endless possibilities. Electromagnetic radiation is emitted due to the thermal agitation of surface electrons. Continuous distribution of frequencies ranging from ultraviolet rays to infrared rays. This is contrary to the case when we heat a gas, because in gas there is a discrete distribution of frequencies ranging from UV to IR, unlike how it is continuous in solids. A black body is a perfect absorber as well as a perfect emitter of electromagnetic radiation. The radiation emitted by a black body when it is at any finite temperature where temperature is greater than 0 Kelvin is known as black body radiation. The intensity of black body radiation depends on frequency and the temperature. The black body radiation curve represents the plot of spectral energy density as a function of frequency or wavelength at a fixed temperature. These curves are also referred to as black body isotherms. Spectral energy density is the amount of radiation emitted or absorbed per unit volume per unit frequency range. Here the frequency is given by the frequency plus the absorbed frequency. This is the spectral energy density on the y-axis, and this is the frequency of an oscillator on x-axis. We can see as the frequency increases, the spectral energy density keeps increasing until it reaches a peak and then starts to decrease after that. Using classical ideas, we were only able to obtain the graph until the peak using the Rayleigh jeans. Only we were able to obtain it until the peak, and after that it was unknown to us using the classical ideas. That is where quantum mechanics came into play. At every certain temperature, there is a frequency of light that is emitted. The frequency emitted is maximum at a peak, as shown here. So the maximum frequency divided by the temperature, absolute temperature at the point, is a constant, which is later defined as the Wien's constant, denoted by the small letter b. We can also rewrite it as lambda max, the wavelength of the emitted light, lambda max, into the absolute temperature is equals to Wien's constant, where Wien's constant is of the value 2.89 into 10 power minus 3 meter Kelvin. Also, the obtained curve of a black body radiation spectrum is asymmetric in nature, which has peak towards the left side and gradually the area increases under the right side. Also, the area under the black body curve, the area which is under the black body curve to the x-axis, uses the energy radiated per unit time surface area. The energy emitted per unit time surface area is given by the integral of the spectral energy density from the limit 0 to infinity, which is also equals to sigma into t to the power 4, where sigma is Stephen's constant and its value is 5.67 into 10 power minus 8 Weber meter square inverse Kelvin power 4 inverse. According to classical explanation, energy between radiation and matter can take place continuously. For a black body, where the temperature is above the absolute temperature, critically that is 0 Kelvin, the thermal excitation of this is the body that we take, and assuming this is the surface, due to us applying the heat to that, thermal excitation of some surface electrons occurs and radiation is emitted. Rayleigh jeans tried to explain this using classical equipartition theorem, and it says energy per degree of freedom. The degree of freedom is the number of ways an atom can move in the three-dimensional space. Energy per degree of freedom is given by 1 by 2 into k into t, where k is a Boltzmann constant given by the value 1.38 into 10 power minus 3 joule Kelvin inverse. For harmonic oscillators, energy is given by kinetic energy plus potential energy. Kinetic energy is given by half mv square and potential energy is given by half kx square for an oscillator. It can also be rewritten as p square by 2m, where p is the momentum, m is the mass, plus half into m into omega square into x square, where omega is the angular frequency and x is the position change or position. Energy per oscillator is given by k into t, and number of oscillators per unit volume per frequency range is given by g nu d nu equals to 8 pi nu square by c cube into d nu, where nu is the frequency, it is a change in the frequency d nu, c is the velocity of light, and spectral energy density is given by kT into g nu, the number of oscillators into the energy per an oscillator, which gives as a spectral energy density, that is 8 pi nu square by c cube into kT into d nu. Now, plotting a graph tells us this is the Rayleigh-Jeans classical explanation, which gives us explanation until a certain correct value. Until here, it gives us the correct explanation, and after that it's just absurd, giving us some infinite values, whereas the observed emission is different from what is theoretically obtained. The Rayleigh-Jeans idea, as observed, only explains for lower frequencies but not for higher frequencies. It is only able to explain for infrared region mostly. The inability of classical ideas to explain black body radiation isotherm in high frequency range is termed as UV catastrophe, which is the birth of quantum ideas. It is where scientists started to think that something is wrong and we must change our ideologies, our way of thinking to obtain the correct results. Now we come to Planck's hypothesis. Planck succeeded in giving an accurate description of blackbody radiation, and UV catastrophe was avoided. Planck was awarded the Nobel Prize for his lucky guess work, the beginning of modern physics. According to Planck's hypothesis, energy exchange between radiation and matter occurs in discrete manner. Energy of radiation emitted by oscillating charges, that is, electrons, from the walls of blackbody cavity must come only in integral multiples of h nu. Energy exchange between radiation and matter take place in discrete steps. The change in energy, delta nu, is given by integral multiples of h into nu, where h is the Planck's constant and nu is the frequency. N can be any integer, 0, 1, 2, etc. And energy exchange is an instantaneous process. For example, in photoelectric effect, even when radiation is incident at high intensity, no matter what the intensity is, whether it's low or high, if the frequency is lesser than the threshold frequency, that is nu naught, as we think, the photoelectrons are not emitted, which implies that the energy which is stored is not being stored continuously, but instead being stored packet-wise. Planck used some harmonic oscillators, now known as Planck's oscillators, to prove this. These Planck oscillators have distribution of energy. Here we write n equals to n0 plus n1 plus n2 and so on, which keeps continuing, which can further be written as summation of n into I, where I runs from 0 to infinite, and E, the energy, is given by sigma I into Ni into Ei, where N is the number of oscillators and E is the energy of an oscillator, which expands for N0 into E0 plus N1 into E1 plus N2 into E2 and so on. Here, E, which is energy, is given by h into nu, where h is the Planck's constant and nu is the frequency. Average energy of Planck's constant oscillator. Energy average is given by the formula h nu into e power h nu by kt minus 1, where h is the Planck's constant, nu is the frequency, k is the Boltzmann constant, and T is the absolute temperature. And number of oscillators, as we have previously discussed, is 8 pi nu square by c cube into d nu. For the spectral energy density, we multiply the number of oscillators into energy of a single oscillator, which is given by the average energy of an oscillator, which is 8 pi nu square by c cube into h nu by e power h nu by kt whole minus 1 into d nu. This is popularly known as the Planck's radiation formula. At lower frequencies, this formula should be related to classical idea of Rayleigh-Jeans formula. Explaining this for lower frequencies, rho nu d nu, the spectral energy density is given by 8 pi nu square by c cube into h nu by e power h nu by kt minus 1 into d nu. And as h nu is far less than kt, we can write h nu by kt is also far less than 1, and e power something which is far less than 1 can be written as 1 plus the power 1 plus whatever the thing is in the power 1 plus h nu by kt, in this case minus 1, and 1 and 1 gets cancelled, and the h nu and h nu get cancelled, so the kt comes up, and as we have previously discussed, the only kt remains, which gives us the Rayleigh-Jeans formula. For lower frequencies, the Planck's formula and the Rayleigh-Jeans formula match. It is because, as we see, e power x expands for 1 plus x power 2 by 2 factorial plus x power 3 by 3 factorial and so on. And it can be written as 1 plus x, which we have done here. But for higher frequencies, as we can see, where h nu is far greater than kt, it is somewhat similar to e power infinity. So here, substituting this, he gives us 8 pi nu square by c cube into h nu by e power infinity minus 1, which is something 0, which is absurd, as energy emitted is never 0 actually, which we observe. Now we move on to the next topic, that is Compton scattering experiment. Compton scattering is the most conclusive experiment to prove the particle nature of radiation. Here, we place an X-ray source and collimating slits with a graphite target and a movable detector along an arc which detects the deflected X-rays. So now what happens is we shoot X-rays from the X-ray source onto the graphite target. Due to its valence electrons, as we know, graphite is made of carbon, and carbon's electron configuration is 1s2, 2s2, 2p2. Due to the valence electrons, the incident light is deflected and scattered in a different path. Along the normal, the average path, it is displaced by an angular displacement of theta, and also the free wavelength slightly changes with increase in scattering angle, that is by how much angular displacement the wavelength actually deflected. The secondary peak becomes more prominent and shifted more towards longer wavelengths. Scattered radiation peak shifts to longer wavelength than source. Wavelength shift depends only on scattering angle, but not on the incident wavelength. As we can see here, the original wavelength is lambda naught. And as we increase the scattering angle from 0 to 45 degrees, we can see that there is a new peak that is obtained, which is higher than the original peak. And the difference in the wavelengths is given by delta lambda. For 45 degrees, it is somewhat near to 0.007 angstroms. For 90 degrees, we can observe it is far greater, and the delta lambda is given by 0.024 angstroms. For 135 degrees, it is given even higher, with delta lambda given as 0.041 angstroms. According to classical ideologies, interaction of high energy electromagnetic radiation with electrons of carbon atoms, which constitutes graphite. Since the energy of X-ray radiation is too high to be absorbed by a free electron, the incident X-ray would then give an oscillatory electric field which sets the electrons into an oscillating motion. Therefore, electrons should emit electromagnetic radiation with the same wavelength according to classical explanation, but with an intensity I, which depends on incident radiation intensity. Whatever the radiation that is incident has an intensity, but through experiments it was observed that the wavelength of scattered X-rays increases by an amount, delta lambda, as we have just seen, which depends only on the scattering angle theta. The scattering angle is very important in determining the peak and the change in the delta and the change in the lambda. So for 180 degrees, it's maximum. Plotting a graph between the scattering angle and the change in lambda. The change in lambda on the y-axis and the scattering angle on the x-axis gives us this, where it attains peak at pi radians, which is 180 degrees, and delta lambda is positive. That is, there is a decrease in energy. Here, inelastic scattering of X-ray electrons happens. Theoretically, the electrons oscillate with the frequency of incident light and emit X-ray radiation of some frequency, but there is instability in emission of energy, so we approach this effect using quantum ideologies. Using the quantum approach, we can see, applying the law of conservation and momentum, the laws in photon energy is equal to the gain in electron energy, electron's kinetic energy, which is given by h2 minus h nu naught, h nu dash equals to k, which can be further written as h into nu minus nu dash equals to kinetic energy. For a particle where we assume m naught as a rest mass and velocity as c, energy is given by rest mass energy plus kinetic energy, where rest mass energy is given as mc square, and as m we take m as the rest mass, we write it as m naught into c square plus kinetic energy, which can be further rewritten as whole root of p square into c square plus m naught square into c power 4. Photons can never be at rest as the rest mass is 0. So even the most negligible energy or even nothing can agitate a photon. So delta lambda, the change in the wavelength, is given by h by m naught into c into 1 minus cos theta, where h by m naught into c for an electron is given by this. This h by m naught into c is also known as Compton length, and it is near to 2.42 picometers, which is 10 power minus 2 meters, 10 power minus 12 meters. for the maximum scattering angle, which is 180 degrees. And for reference, 180 degrees means the X-ray which is incident on graphite retraces back on the same wave on the same path as it has been incident. So for that, the lambda max is given by the Compton length h by m naught into c into 1 minus cos of phi. Cos 180 as we know is minus 1. So 1 into minus 1 of 1 is whole 2. So 2 into the Compton length is 4.84 picometers. That is 4.84 into 10 power minus 12 meters, which is the max shift in the wavelength. Here maximum transfer of energy between photon and electrons takes place, that is at phi, that is scattering angle at 180 degrees. Compton effect can take place for any kind of electromagnetic wave. We can't observe Compton effect for all electromagnetic waves as a relative shift, that is the shift in the wavelength by the original wavelength, is 0 for visible light. Compton effect only occurs for free electrons, while photoelectric effect only occurs for bound electrons. It is due to the difference in incident wavelength of frequency. Moving on to de Broglie's hypothesis. According to de Broglie, nature loves symmetry. And in 1925, he suggested that matter may have properties like wave, and he put forward these ideas in 1925, leading him to winning the Nobel Prize in 1929. So according to him, if light, which behaves like waves according to classical physics, can exhibit particle-like behavior, then it should be possible for matter, which classically behaves like particle, to exhibit wave-like behavior under suitable circumstances. This wave-like behavior for matter is represented by matter waves. So here we come to the famous formula, that is the lambda by hp, which is derived in the following way. The relativistic energy of a particle of rest mass m0 is given by energy equals to root of p square plus c square plus m0 square into c power 4, as we have discussed earlier. For photons, the rest mass is 0, as photons can never be at rest. E is equals to p into c, as we obtained from this, and rewriting this as p equals to e by c, and according to Planck's hypothesis, E equals to h nu. So nu can be written as c by lambda, and E by c gives p, which is h by lambda. There we come to the famous formula, lambda is equals to h by p. Since this relation holds good for radiation, it must also be applicable to a particle having momentum p. This hypothesis, prescribed by de Broglie, is known as de Broglie's hypothesis. De Broglie wavelength for matter waves associated with moving particle of energy E and momentum p is h by p, and p is given by root of 2m into kinetic energy. Now we come to the properties of matter waves. Matter waves are associated with moving particles only. The corresponding wavelength for the matter waves is known as de Broglie wavelength. The particles with higher momentum are associated with shorter de Broglie wavelength. The quantity whose periodic variation makes up matter waves is known as wave function. This wave function plays a very crucial role in quantum physics. Now we come to discuss about the Davisson-Germer experiment. This experiment proved de Broglie's hypothesis and the matter waves. Here, a tungsten filament which has a high thermionic emission is placed and is heated, and it emits a beam of electrons which is then accelerated to a high potential, and it is hit on a nickel plate, and then these electrons are reflected and it is incident on a movable electron detector. Crystals consist of regular periodic arrangement of atoms along the lattice planes. As we know, X-rays are reflected by these lattice patterns and exhibit diffraction as their wavelength is nearly of the same order as the interplanar spacing d. The diffraction maxima occurs when the path difference is 2d sine theta and an integral multiple of incident X-ray wavelength lambda is known as Bragg's law. Bragg's law is given by 2d sine theta is equals to n into lambda, and we can see this is the lattice pattern of each layer of a particle or a matter or substance, whatever, and the wave that is incident hits a particle and gets reflected. The amount of angle by which it is reflected is known as the reflected angle, and for two different layers there is a difference in the heights, and this is known as d. And we use the trigonometric ideas to obtain this equation 2d sine theta is equals to n into lambda. In the apparatus, Davisson and Germer used nickel crystal which has interplanar distance of 0.091 nanometers by replacing X-rays with a beam of electrons to verify the existence of matter waves. Low energy electrons of nearly 54 electron volts are scattered from single crystal of nickel and are detected in ionization chamber. Instead of a diffused pattern expected as per as classical ideas, the reflected electrons form the diffraction pattern that is very identical with X-ray diffraction. According to the polar graphs, we can observe for 40 electron volts, the shift is minimal. For each increasing energy, the shift seems more apparent. For 44 it's this much, for 48 electron volts it's this much, and it is found to be maximum at 50 degrees, where the obtained energy is 54 electron volts and the angle observed is 50 degrees. And beyond this, the bump again started decreasing. Like beyond 54 electron volts, the bump again started to decrease further and further and further. Since the kinetic energy of incident electron is 54 electron volts, the corresponding de Broglie wavelength of the matter wave associated with these electrons is given by lambda equals to h by p, where p can be written as root of 2 into m into kinetic energy, and it is further written as the Planck's constant, which is 6.625 into 10 power minus 34 by whole root of 2 into 9.1 into 10 power minus 31, where 9.1 into 10 power minus 31 is the mass of an electron, 54 the energy in electron volts, which is to be converted into joules, so we multiplied by 1.6 into 10 power minus 19, which on further calculation gives us the value 0.167 into 10 power minus 9 meters, which is also as written as 0.167 nanometers. Excellent agreement between experimental design and de Broglie's hypothesis proved that de Broglie's hypothesis was real and true, and matter waves do exist and are associated with all the moving objects. Quantum ideas and quantum physics is a very diverse and big branch which gives us logical explanations for all the things which you previously didn't know, and these ideas will be further studied and will keep diversifying and increasing even in the future. Thanks for watching and have a nice day, everybody.